Hi, welcome to my channel, JaberTime. Today I'm going to go over Stokes Theorem. I'm going to show you what is Stokes Theorem. And I'm going to go over one example in 3 different ways. Hopefully you'll like it. I will slow down this time, connecting 3 different ideas for one example. In the coming future, I'll be adding more examples for each section. For sure, Stokes Theorem is one of them. So let's get into it. Stokes Theorem can be regarded as a higher dimensional version of Green's theorem. The double integral of curl f dot ds is the line integral f dot dr. In Green's theorem, it was in a plane. Stokes' theorem is in a 3 dimension. It's over a surface, where Green's theorem was dealing from a line integral to a region D. So you could see clearly that Stokes' theorem is like Green's theorem, but it's a higher level, higher dimensional version of Green's theorem. Green's theorem relates a double integral over a plane region D to a line integral around its plane boundary curve. I covered that with examples in earlier videos if you need them on my playlist. Stokes' theorem relates a surface integral over a surface S to a line integral around the boundary curve of S. See this right here? This curve C is the boundary curve of S, which is a space curve. The following figure induces the positive orientation of the boundary curve C, shown in the figure right here. This means that if you walk in the positive direction around C, see this person walking this way? Around C, which is a surface curve, not a plane curve. With your head pointing in the direction of N, which is the normal, then the surface will always be on your left. That's called positive orientation. So what's Stokes' theorem? Let S be oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Let F be a vector field whose components have continuous partial derivatives on an open region R to the third that contains S. Then the line integral f dot dr along the curve C becomes the double integral of the curl of f, which is a cross product, dot ds. We learned how to find the curl, how to find the divergence. Now we're using Stokes' theorem to apply it. Let's be practical and look at an example. This example is a great example, and that's not going to be enough. But in the meantime, I think that's going to be enough. In the coming future, I'll be adding more examples, but I don't want to make the video, as I said, 45 minutes to over an hour. This video is designed to clear up the concept of Stokes' theorem with a great example. Later on, I'll be adding more examples. That's a promise. Here we go. Evaluate the line integral f.dr along the curve C, where the vector field f is minus y square I plus xj plus z square k, and C is the curve of the intersection of the plane y plus z equals to this blue plane, and the cylinder, which is around here in gray, x squared plus y squared equals 1. Orient C to be counterclockwise, as we saw earlier in the default graph, when viewed from above. Now, as I mentioned earlier, I'm going to do it 3 different ways, and I'll do my best to speak clearly and slow down. Here's the first method, directly. So we're using line integrals from the first 2 sections of this unit, when we talked about vector fields. Then we talked about line integrals. To do it directly, we could change f.dr to f of r of t dot r prime of t dt. If you need to know more about line integrals, I do have line integrals video in the playlist of this videos. R of t, to represent C, we're going to represent it with cosine t, sine t, 2 minus sine t. Notice that z equals 2 minus y. That's 2 minus sine. Y will be sine and x will be cosine. 1 times 1 times, because r is 1. We're tracing the line C. Now, this is the vector field that was given to me. Let's find r prime. I have f. We're going to change it to r of t. We're going to do r prime. And we're going to do the dot product. If this is r, r prime will be minus sine, cosine, minus cosine. 2 will give you 0. The derivative of sine is cosine, but I have a minus, so it's going to stay minus. So I have this part right there. Since I have f of x and y and z, we need to parameterize it and write it in terms of t, or r of t. F of r of t will equal to, let's take a look at this right here. This is x. And x is what? Cosine of t. In the middle with the j component, it's x, which is cosine t, right there. The first part is minus y squared. This is my y component, minus sine squared. Z squared, that's 2 minus sine being squared. Let's do the dot product between the 2 circled ones. That's f, and that's r prime right there. Here's the dot product. Once you have them lined up, as you could see, it's easier to multiply. Multiply this by this, multiply this by this, multiply this by this, and add them up. And that's what I have. Now, I want to simplify, and I want you to follow the steps. I could skip the steps, but I want to take care of it. We do the 2 minus sine to the second, kind of like a minus b to the second becomes a squared minus 2ab plus b to the second, and that's what I have. So it's 4 minus 4 sine plus sine squared. Now I'm going to distribute this over the 3 terms. Slow it down so you could follow me and see it and believe in it. Now I'm going to take you to the first part, which is minus sine cube. One way to handle integration of sine cube, or actually the best way, is write it as sine and sine square. So now the focus is on this part right here. But sine square is 1 minus cosine square. That's this part right here. Doing the distributive right here, I have the following. Now we are ready to go back to the problem and integrate f.dr, which is integrate of this with respect to dt. That's this whole thing that we found. f.dr is the integration of f of r of t dot r prime of t, and I need to integrate all this. I have different colors to tell you which one is which, so you could stay focused. Minus sine will give you cosine, and so on and so on. Using u substitution here for cosine being the u part. Cosine square will give you 1, the formula that I used earlier. We have 4 cosine, we have 4 sine cosine, u substitution. We have sine square cosine, u substitution for sine. I'll just give it a few seconds so you could look at and follow. Of course, after that, plugging in 0 and 2 pi is not too hard or time consuming, but I'm taking the time to display it instead of say it. And here we go. Simplifying, it ends up as pi. Now, let's move on to another method, which is this lecture topic, Stokes Theorem. By Stokes Theorem, we're going to do the curl of f. Let's parameterize the surface S that was on the graph. So we have R of u and v is u and v and 2 minus v. In general, instead of calling it x and y and so on, this is my parameterized curve. Slowing down because all the previous videos becomes so handy now following those steps. R of u is 1 and 0 and 0. With respect to u is 1, with respect to u is 0, with respect to u is also 0. Derivative of this with respect to v, that's a 0, that's a 1, that's a negative 1. Of course, you know what we need to do next, and that's called cross product. Doing the cross product to find the n part, the normal. That's an easy cross product. It has a lot of zeros and ones. That's our cross product. Now to find the curl, which is another cross product between the gradient or del and the components of f. We end up with the following: 0, 0, 1 plus 2y. Now I have this circled in green and I have this circled in red. We're going to go back to the problem. Now let's do a dot product between these two. That's a quick dot product. You multiply the corresponding components and add them up as a scalar. It's just 1 plus 2y. Now my parameters are u and v in general. But to be clear with our graph, we could use polar. So my parameters are r and theta for polar. We change y to r sine theta. We are down on the disk below as an area, so y is r sine theta, where r ranges or changes from 0 to 1 and theta goes from 0 to 2 pi. Taking care of the first integral with respect to r, theta is constant in our point of view for now. It's not too hard to integrate r plus 2r to the second times a constant with respect to r. Plug in 1 and 0. R to the second becomes r to the third over 3, and r becomes r to the second over 2. We leave this alone. It's a constant. Plug in 1 and plug in 0. There's no need to plug in 0. It's going to cancel. Now integrate this with respect to theta and plug in 0 and 2 pi. Plug in 2 pi and plug in 0. Simplify. Instead of reading it, I'm displaying the whole thing for you. Simplify. Last step. Same answer. Hopefully that was helpful. But now I want to show you a different way. Going back and forth and now connecting the sections together and the videos together, we could apply the following method. Here we go. We're going to treat curl f as a new f. Just stick with me and you'll know what I'm talking about because I have the notes all displayed. Here we go. This is the formula. 2 videos ago was mentioned. You need to use it when you can. That's when your function z could be written as g of x and y. And here we go. The double integral f dot ds on the surface in 3 dimensions could be translated to the region D. dA, whatever dA is, polar or rectangular, whatever you have, minus p g of x. G, x means the derivative of g with respect to x, the partial derivative, minus q g sub y, the partial derivative of g with respect to y, plus r by itself. And here we go. We have x squared plus y squared equals 1. We have y plus z equals 2. That's the plane on top, the surface. And this is a cylinder. So from the second one, from the surface, trying to make it fit here, that's why I didn't put the graph here again. I could write z as 2 minus y, taking advantage of this form, which is z equals g of x and y. That's my g of x and y. Even though it doesn't have an x in it, but I could still use the concept. Meaning, g of x is 0. The derivative of g with respect to y is negative 1. You could see it clearly. Is our vector field. That's not my new f. That's my vector field. The curl of f, which is a cross product between del and f. We've done it before. You do the math. We get 0, 0, 1 plus 2y. New f. This is the curl of f. And this will be our new f, as I mentioned on top. So it's 1 plus 2y k. Notice it has a k component in this case. No I, no j. Usually, vectors in 3 dimensions, we call them pi plus q, j plus rk. Our new function is 0i plus 0j. There is no I or j components, and 1 plus 2y, the k component. Go back to the problem. This is the formula. And now this is our new function. Notice that this p right here is 0. Earlier, p is minus y squared. So we're not using the vector field itself. We're using the curl of f as a new f. If we treat the curl as a new f, and you could write z as a function of x and y, you could use directly this formula and you'll be fine. G of x is right here 0, g of y is right here -1. It's right there, and it's right here, green, 0, 0, 1 plus 2y, not z squared. After that, it's regular math. It's a double integral of just 1 plus 2y because these cancel. Of course, you have to know what's dA and what's the region D. We know the graph and we know the region D. Go directly to the polar form. R changes from 0 to 1 and theta goes from 0 to 2 pi. This is exactly the same that we had in the second method when I called it by Stokes theorem. So I'm not going to repeat the steps. I'll just show you the steps right here. This is what we had, exact same steps from that slide. So we'll just copy it here, look at it, and believe in the answer as being the same, which is pi. Hopefully that is clear. I tried not to go too fast, and I tried to stay focused with you. In the coming future, more examples will be coming to Stokes theorem. In the meantime, to stay focused, I think this example, doing it 3 different ways, helps understand the Stokes theorem, the line integral, and z equals g of x and y concept. Thank you, and I'll see you next time. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.